All right, people. Oh, I know I'm a little got poor lighting in here, so I might look a little spooky. But anyways, let's talk about in our last video. We mentioned Ernest Rutherford had discovered the nucleus with his gold foil experiment, but I think I was wrong on that. He didn't discover it because of his experiment. He had the idea of the nucleus before he did the experiment. So he did the experiment to kind of prove himself correct. He didn't do the experiment and then was like, hey, let me explain what the experiment happened. So this was actually him doing an experiment to explain his theory, which kind of just shows his brilliance, that he had some ideas going in there. Now, one thing I didn't talk about was Robert Millikan. Now, Robert Millikan discovered the actual charge of the electron, right? And I'll give you guys a little quick rundown on what he did. The book has a better explanation, but just imagine a container in here, right? Just a regular old container, and then in here, you have a little filter with a bunch of tiny little holes. All the same size, right? Well, all the same size, right? Just imagine a bunch of tiny little holes right here in one area, all the same size. And then you have some sort of source of radiation that sends X-rays. Now, X-rays were discovered at the time from messing with uranium. So they discovered that X-rays and that this radiation, these types of radiation that was coming out, would charge the particles. So the oil would come down and they would get charged by this X-ray hitting them. So now all of these oil particles that are getting dropped over here, so you have some oil over here, going through, and they now have a charge. And then under here you have a barrier where there's an electric field or a magnetic field, and that magnetic field is going to interact. Later on, when you guys learn about some physics, some electrical stuff, magnetism and electricity go hand in hand. So if you have a magnetic field, it's going to affect how charged particles will move. So basically, these oil droplets were caused to shift, and that shift allowed the mass to be calculated for the electron later on, because they knew the mass to charge ratio from J.J. Thomson. So if you know the mass to charge ratio, if you can figure out the charge, well, then you can figure out the mass. And that's what happened. The particles that were emitted here had a +2 charge. They're called alpha particles. And we're going to talk about alpha, beta, and gamma particles later on. Way later on, if we get to it. But anyways, that's just Robert Millikan's experiment. I didn't really talk about it that much last time. Another important discoverer was the one that discovered the neutrons. We're not going to talk about his experiment, but his name was James Chadwick, and I believe he also was a understudy of Ernest Rutherford. So the neutrons. Wait, no, the neutrons took a while after him to be discovered. Yeah, so the neutrons were discovered 30 years after the proton was discovered. So I think I explained in the last video where the proton was thought to have twice as much as the weight that it actually has. But in reality, it's the neutrons that have that mass, and they're just both located in the same spot. But anyways, all three of these particles end up making everything in existence, right? All atoms are made out of protons, neutrons, and electrons. And each of these particles behaves differently. Electrons were found to be very, very small and mostly empty space. That's why things went right through the atom during Rutherford's experiment. However, the protons were heavy and tiny, so they had a lot of mass, but they're very small. And they were in one tiny little location. Same thing with the neutrons. The neutrons had the same mass of the protons, but no charge, and they were found in the same spot. So now all of the mass is discovered in one tiny little section of the atom, and all of the space is found created by the electrons. The electrons would be like this cloud that surrounds the nucleus, and that cloud is very, very low density because the electrons are very, very light. All right. Now, that's what these next slides say, right? The nucleus is small, and it is extremely dense. One thing I want you guys to think about, if the atom is like a cloud, right? The electrons are like a cloud going around, and there's like all these negative particles around it, but inside there's positive particles, right? And we have this fundamental idea that like opposites attract. So like positives attract negatives. So why don't all the electrons go straight to the protons? Like, why don't they just go shoot towards the center? I don't know. Think about that. And then why is it that the nucleus has all these protons in it? And when you get two magnets that have the same charge, they don't want to touch. They push each other away. So why is it that these things can be inside of a nucleus without them falling apart? Now, all of these questions that you probably have, they have very, very complicated answers. And if you want to learn that, you got to keep studying some physics, study some chemistry, and then, it gets wild. It gets wild, but it's really cool stuff. All right. But anyways, let's think of like the atom, right? The atom is a cloud, and the nucleus is a very, very small portion of the whole atom. And this is just a little visual. In reality, it's not like smooth circles like that. They're kind of just like wavy. And I think this is an exaggeration of the nucleus size. This is too big for scale. All right. All right. Now, let's go back. That's our idea. Now, back to Dalton's theory. With Dalton, we had said that Dalton was wrong. He was wrong about all atoms being identical. And the reason he was wrong is because isotopes. The way to think of an isotope is it's like having a twin brother. Everything appears to be the same, but there's slight differences. For example, weight. If you have like a twin, exactly like you, same DNA, same everything, the building of the person is the same, but how much they weigh is differently. And atoms are just the same way too. Some atoms are slightly heavier because they have additional neutrons, right? So neutrons, they don't change the chemical identity or the chemical properties. All they do is change the weight. For example, you can have a hydrogen with a H1, H2, H3. There's 3 different types of hydrogens. And then the heavier hydrogens, the heavier hydrogens are used to make heavy water in like radioactive like power plants and stuff. They use heavy water in reactors, which is kind of cool. The isotopes can also be used differently. Some of them are radioactive, some of them are more radioactive, some of them decompose into certain products that you want. Some isotopes become very unstable, and that's why they're radioactive. For example, carbon-14 is radioactive, and that's what's used for carbon dating. The most common carbon that we have is carbon-12. Carbon-12 has a mass of 12 AMU. 6 protons, 6 neutrons, add up to 12. This one, however, has 6 protons and 8 neutrons. All right, so the mass always comes from the protons plus the neutrons. And the protons, if you ever forget, remember, check your periodic table, it's always the atomic number. The atomic number never changes, so the protons never change. It is its identity. The only thing that can change is the mass, and that comes from the neutrons. All right, let's continue showing some stuff. All right, later on, we're going to talk about how electrons affect things. I think that's the next section. Electrons are responsible for chemical reactions. Protons and neutrons, changes in them, are responsible for nuclear activity. But how do we write this? All right, so you have a symbol here. This would be your chemical symbol. So let's just use the example of carbon. The mass number is the mass of the protons plus the neutrons. So let's say carbon 14 has a mass of 14, so we'd write it there. And it has an atomic number of 12. No, sorry, 6. Whoops. Yeah. So this has 6 protons, and then the protons and neutrons added together add up to 14. So carbon 12 is going to be like this. Pretend that looks like a C instead of a G. So it has 6 protons, and then a mass number of 12. So 6 protons, 6 neutrons. All right. Now, let's think of some things. Example here of sodium. Think of, this is nicer. This is nice. This is a lot nicer than my drawing. All right, so the nucleus, you have, we're taking a look at sodium, right? Sodium 23 and sodium 24. The only thing that changes is the number of neutrons, right? Because the electrons don't change. The electrons change when the charge changes. All right, so if you see like Na plus, well, that tells us we're losing electrons. If for some reason you see Na minus, well, that's telling you that you're gaining electrons. So electrons affect the charge of the atom because they're the ones that come and go. They're on the outside, so they can leave. The protons never change when charges change, okay? Just something to keep in mind. But, yeah, what do I say here? And that's kind of it, I guess. It's a short video. But learn to write things down in this notation. Another way you might see things is like this. So this would be sodium and then 24. All right, or this would be sodium 23. All right, that's not a minus sign, that's a hyphen. All right, it doesn't look like a hyphen, but pretend it is. All right, now, yeah, that's it. Let's see, is there anything I'm forgetting? Oh yeah, there's a table on page 47. I want you to write that one out. Just write down the mass of the protons, the neutrons, electrons, and its charge. All right. Did I forget something? Ooh, heaviness of the atom. Proton's super heavy. It's like 1,000 times heavier than the electron. Protons and neutrons basically have the same mass, just different charge. I think last video I explained how through some nuclear process, protons can become neutrons, but that's some more advanced science. But peace out, people. Take it easy.